Vicky did his undergrad at IIT Kharagpur in aerospace engineering. Then after that, he acquired some industry experience for a few years in computational fluid dynamics modeling simulation. Following that, he did his master's at Jawaharlal Nehru Center for Advanced Sciences in Engineering Mechanics, where he did research in gas dynamics. Then he did his PhD in UCSD University of California in San Diego with Sudaman Sarkar, and there he transitioned more into the ocean, I believe.
Yes, start of oceanography.
Yeah, and he worked on sub-mesoscale dynamics, which we'll touch on today, and also its interaction with turbulence. And since 2022, he's been in Tel Aviv University in a postdoc with Roy Parkat, working on sub-mesoscale dynamics in the Eastern Mediterranean, and I think today also does about general circulation there. So, thanks.
Thank you very much, Aviv. And also, I would like to thank the organizing team for inviting me, and thank you for being here. Today, I'm going to present a part of my postdoc research with Roy Barkan and Yaron Toledo from Tel Aviv University. There are other collaborators also there involved in this project. I will mention them later in the presentation. So the work involves studying instabilities in the Eastern Mediterranean boundary current, how the spirals form through these instabilities. And the later part of my presentation, I will also talk about how the crossroad transport by these features help explain the spatial variability in the chlorophyll concentration that we observe offshore of Nile Delta. So near surface current play a crucial role in transporting and dispersing buoyant pollutants such as oil and tracers such as oxygen and other biogeochemical tracers. The figure, this is a satellite image showing a surface oil in the Gulf of Mexico. From deep water horizon oil spill that happened around 10 years ago. As we can see, the oil slick is being spread by the large scale current in the ocean. Most of these oil finally end up in the coastal region where they damage the rich coastal ecosystems. The figure on the right is a satellite image of chlorophyll concentration in the Arabian Sea. Again, we see imprint of currents and eddies over a wide range of scale on the chlorophyll concentration. So in the ocean, the primary production is primarily done by phytoplanktons, which are micro scale features, and for the production, they depend on sunlight as well as the nutrients in the upper layer. And as these currents and eddies swirl around the phytoplanktons and the nutrient, leaving behind their imprint on the concentration map. So if we want to understand these complex processes, understanding of the surface current is very important. So Mediterranean Sea is one of the most important regions in terms of trade. About 1/3 of the world trade passed through this sea. As a result, many ships and oil carrying tankers transit from the sea, and the oil spillage is an acute problem in this region. This figure shows major oil spill in the Mediterranean Sea between 1977 and 2017, and we see there is a hot spot of the coast of Israel. So one such incident took place in early 2021, when a large quantity of oil was spilled offshore of Israel. Some of the oil washed up to the shore in the form of tar and affected around 180 kilometers of coastline in Israel and Lebanon. However, some of the oil remained in the sea, which disintegrated into small patches and this again disintegrated into small patches, and they dispersed hundreds of kilometers offshore from the source region, as shown by these and observed in these satellite images. So they disperse quite away from where they get where the spillage happened. So this kind of suggests that the dispersion occurs through a complex process. So Lagrangian drifter experiment conducted in the Gulf of Mexico around about 10 years ago highlights some of the processes that are involved. During the experiment, a large number of drifters were released in the ocean. Some of the drifters shown in black circles, these were transported and dispersed by the large scale current. However, some of the drifters shown in magenta color in these figures, they converged on a thin filament whose width was less than 1 kilometer, which then wrapped around a cyclonic eddy. Eventually, this drifter ended up in a small region of diameter around 60 meters. After a few days, this feature disintegrates and then they start to disperse again. So these two different behaviors by the drifter can be noticed in this PDF of pair separation. The top branch shows the drifters which are advected and by the large scale current, and they disperse from the beginning, and the pair separation increase after they are released. On the other hand, the lower branch shows drifters converging in these small structures. As a result, the pair separation initially decreases, but they start to increase eventually. These two images show the pair separation period for the two groups of drifters separately. Essentially, the picture we get is the transport and dispersion of material by the large scale current, and embedded in this current we have this structure which we call submeso scale structure. Typically, we associate length scale range of 100 meter to 10 kilometer and revolution time scale of order 1 day to these features, these submeso scale feature. And embedded in the large scale currents, we have this submeso scale structure where the materials accumulate as opposed to spreading away from one another, as in the case of non-divergent large scale currents. And in order to capture the dispersion, surface dispersion properly, we need to resolve a wide range of scales from the basin scale down to the submeso scale, which makes this problem quite challenging to study.
Just Vicky, just a remark, your speeds, given your maximum length scale and time scale is about 10 centimeters per second. Just for the atmospheric scientists in the crowd, the speeds are 10 centimeters per second.
No. So for submeso scale, it can be the currents can be stronger.
Yeah, but order 10 centimeters. 10 kilometers in 1 day is about 10 centimeters per second. Right?
Yeah.
About. So just let the atmospheric scientists really
Okay.
what you were talking about.
Sure. Thank you. A little bit more about submeso scale regime in the ocean. As I mentioned, just now, they correspond to the scales of motion in the range of 100 meter to 10 kilometer, an evolution time scale of order 1 day. Dynamically, they are associated with motion that are order 1 Rossby number. U is a horizontal velocity scale, F is the Coriolis parameter, and L is a horizontal length scale. As well as order 1 Richardson number, N is the buoyancy frequency here. So this means that the flow inertia is not negligible at these scales. And what do they look like? Typically in the upper ocean, they are generated by pyroclinic mixed layer instabilities, and they appear as a soup of cyclonic filaments and eddies, as shown here in the Gulf Stream region. So these cyclonic filament and eddies are similar to the structure observed during the drifter experiment, the convergent filament which wraps around the cyclonic eddy, and they are basically they are the oceanic counterpart of the weather system in the atmosphere. But however, since the length scales are small, so we can have many of them in the ocean. In the interior, we get what we call SCVs, the semi-mesoscale coherent vortices, and they are basically eddies generated by the separation of a boundary current from a bottom topography, such as the formation of an anticyclonic eddy shown here. However, as I will discuss in this presentation, we also form these eddies through boundary current instabilities, and to distinguish them from the typical mixed layer eddies and SCVs, we call them spirals. So back in late 1980s, a series of field experiments were conducted in the Eastern Mediterranean to better understand the general circulation in the region. The flow features that were identified from the hydrographic data were compiled in a schematic shown here, which I have taken from Robinson et al. 1991. Basically, the general circulation was described in terms of wind-driven gyres such as roads, permanent and recurrent eddies such as Mersa Matruh and Sikmona, as well as offshore and along slope currents. However, the station resolution were poor along the eastern boundary and southern boundary, so the full extent of the boundary current was not revealed. Only the Silesian current at the northeast corner and the Asia Minor current along the northern boundaries were identified. Later, through high resolution satellite data, a basin-wide boundary current was confirmed using a large number of SST images. Hamad et al. Infer basin-wide boundary current as shown in this schematic, which was kind of inspired from the kind of boundary current they were familiar with in the Western Mediterranean. Later, combining sea surface altimetry data and drifter trajectories, Mena et al. Generated a map of the surface current in the Levantine basin and a boundary current flowing around the Levantine is clearly noticeable. In this SST map, we also notice instabilities in the boundary current, which result into the formation of these eddies. However, a systematic study of the boundary current instabilities are still
This sea surface temperature now, right?
Yes.
So how do you infer the current from it?
So that was done
So
indirectly.
the temperature is a
you
passive
can,
tracer?
kind of, you can imagine temperature as a passive tracer and try to infer. And this was also inspired from the Western Mediterranean. They had a boundary current. They had known that there was a boundary current in the Western Mediterranean, so that helped them to come up with this map. But it was using sea surface height, we can actually compute the surface current and shows there is a boundary current in the circling around the Levant basin. However, we don't know much about these boundary current instabilities. Questions such as what makes the boundary current unstable, what are the instability mechanisms, and how do the instability affect the crossroad transport are some of the questions that require further investigation. So there have been observations of submersible scale features in the Eastern Mediterranean. These images are sun glint images taken from International Space Station using handheld camera back in 1980s. Clearly, convergent cyclonic filaments and cyclonic eddies have been identified in various parts of the Eastern Mediterranean, such as off the coast of Egypt, south and northwest of Crete. Despite this early sighting, however, to best of our knowledge, a systematic study of the submersible scale dynamics in the Eastern Mediterranean was performed recently by Sorodok et al., where they show a space filling submersible scale currents in the domain during fall and winter season. However, these features disappear during the summer. This seasonality of the submersible scale dynamics is well known and have been observed in other oceans. However, again, the interaction of these submersible scale features with the boundary current and how this interaction affect the boundary current dynamics and the crossroad transport is again not well known. One more thing I want to highlight is that submersible scale dynamics are known to affect the primary production in the ocean. As shown here, this is cyanobacteria bloom in the Baltic Sea, and we can clearly see the imprint of submersible scale convergent filaments and eddies on this bloom. Typically, two local processes have been considered or two local processes are attributed for this kind of influence. One is the vertical flux of nutrient-rich water below the mixed layer by the submersible scale currents, and the restratification of the mixed layer by these currents. However, in this presentation, I will show that horizontal stirring by the submersible scale current of the nutrient-rich water can also affect the primary production in a region, especially in a nutrient deficient region such as Eastern Mediterranean. So this brings me to the outline of the today's talk. First, I will describe the numerical model that I am using. I will elaborate the grid nesting that we use to generate high resolution solution. I will also provide a few examples of model validation. Then I will move to the problem of boundary current instability. Here I will discuss the seasonal change in boundary current, its vertical structure, qualitatively, I will describe the boundary current instability and how that leads to the generation of spirals. Then I will elaborate on how the bottom interaction with the boundary current leads to vorticity generation in this system, and elaborate on the instability mechanism by analyzing the energy routes through which the instabilities are energized. And in the later part of this presentation, I will show that how boundary current and the boundary current and the spirals and their interplay with the submission scale dynamics help us explain the spatial variability in the chlorophyll concentration that we observe offshore of Nile Delta region. And then I'll end the talk with a few conclusions. So we have used Croco model to perform a realistic simulation of the Eastern Mediterranean. We have used 3 levels of grid nesting to generate high resolution solutions. At 3 kilometer resolution, the domain, the horizontal domain encompasses almost the entire Mediterranean Sea, and we have used 80 levels at this resolution. The model captures the large scale currents, but the submission scale dynamics is, as you can see, is not well captured. Then at 1 kilometer horizontal resolution, with 120 levels, the domain encompasses the east, almost the entire Levantine basin. As you can see at this resolution, the submission scale, large submission scale filaments and cyclonic eddies are resolved, but they appear to be relatively stable to rollouts. At 300 meter resolution and with 150 levels, the domain is the eastern part of the Mediterranean Levantine basin, and at this resolution, we have many more submission scale features in the domain, as high resolution allows to better capture the frontogenesis dynamics and the submission scale filaments and are much more prone to rollers at this resolution. So we generate these multitudes of cyclonic eddies in the domain. The top figures show a comparison of sea surface height from satellite measurement and from model, and both of them compare well, suggesting we suggest that a large scale flow is consistent with what we observe with altimetric data. Here so the surface current is along the iso contour, and from these figures we see that indeed in our model there is a boundary current which goes around the Levantine basin. Again, we have compared.
This is sea surface height, not this is.
The
map says sea surface height.
Yeah, sea surface height. Or sea surface height. And we also compute kinetic energy at the surface and compare that to model, and again we get pretty good comparison. For a more comprehensive validation with reanalysis data, satellite data, and deep lab velocity measurements, please refer to our recently published paper led by So effectively what we find is that our model result is our model solutions is doing pretty good in capturing the actual flow physics in the ocean. So before we jump into the results, here we visualize the flow structures by plotting vorticity near the surface.
This is region 2, right? The model.
This is the 1 kilometer. 1 kilometer. Yes. Yeah, 1 kilometer model. So as we can see in this animation, we can clearly identify a boundary current going around the basin. We also notice cyclonic filaments and submesosphere cyclonic filament activity filling up the domain. However, as summer approaches, these submesosphere features disappear from the interior of the domain, and the flow is predominantly dictated by the boundary current. Again, we see the boundary current going unstable and generating anticyclonic eddies, which I am also calling spirals. And as the winter sets in, we again start to see the submesosphere features to come up, which happens around November.
So in summer you only have those small scale features in the Ionian Sea, not in the Eastern Mediterranean.
Excuse me.
In the summer, you only have those small SCD, which you call SCD, in the Ionian Sea and not in the Eastern Mediterranean. Is it wind driven or what?
Okay, I'll come.
The Aegean, you mean? The Aegean Sea? You mean the Aegean Sea?
I'll come back to those questions in a bit. Here I have plotted the seasonal wind surface current at 5 meter depth. The winter season corresponds to December, January, and February months of year 2017 and 18, and summer figure corresponds to June, July, and August months of 2018. So in both these figures, we identify the boundary current going around the Levantine basin. However, we also notice some differences. In winter, we have eastward current in the middle of the domain, which gets replaced by a southeast current going across the domain. We also notice that in summer, the boundary current is shifted more towards the coast than in winter. Next, we analyze it. So these have implication when we discuss the bottom interaction. So let's look at the vertical structure of the boundary current by taking a vertical section at 3 different locations. These sections are taken such that the flow direction is perpendicular to it. The velocity maps are shown at the top here. The top row correspond to the winter season and the bottom to summer season. Again, in both winter and summer, we find that the boundary current goes to the depth of about 200 meters in both seasons. However, in summer it is more surface intensified than in winter. We also notice we also notice that the surface maxima moves towards the shore, which makes the profile a bit asymmetric in summer than in winter. Also notice that the boundary current is about 60 kilometers wide. Here I have plotted the volume flow rate. So in winter and summer the flow rates are high, slightly higher during winter than summer, and the values reach as high as 2 to 3 Fahrenheit, which is quite a lot. And in the transition period, we find that the boundary current gets somewhat weaker.
So this increase in flow rate, is it due to the deepening or the increase in speed? What happens to the speed?
Yes, speed increases and also, yeah, both of them.
Both?
But the effect I am showing is because of the speed, increase in speed. So here the boundary current is more spread out, and in summer more surface intensified. But if I but the average of area average of this flow velocity basically is large in winter. So in average sense, the speed is large.
This is based on 1 year simulation, right?
Yes.
So 1 winter, 1 summer. So can you make any strong conclusion based on that? Could it
So
be
yeah,
just internal variation?
we expect these dynamics to be representative of all years. There can be some variability, but they gave, but overall they give a representation of the yearly variation pretty well.
The forcing is climatological.
Yes.
It's climatological.
Yeah, even if you run it with the same climatological, I would expect to get some variability, right? If you repeat it year after year, you won't get the same, right?
Yes,
Some kind of variability exists in the model.
But the overall trends that we are discussing is not going to change. Numbers might change, but the trends look similar to what we are discussing here. So boundary current instability leads to formation of spiral. This top left figure shows a composite vorticity map from 1 kilometer and 300 meter solution. And here we see the spirals, nice spirals forming along the eastern boundary. As we saw in the movie, these spirals are in fact formed throughout the basin. However, how the spirals form is much more clear during summer when the submersible skills currents are not present in the interior. We find that what happens is we find that negative vorticity is generated in the shoreward flank of the boundary current, as you can see here and here, which then becomes unstable and roll into these eddies, which we call spirals. So these eddies play an important role in material transport, and their vertical structure is of importance. This figure shows the vertical structure of a winter eddy, and we find that the spiral goes down to the depth of around 200 meters in this season. However, in summer, the spiral only goes up to the depth of 50 meters, corresponding to the surface intensified part of the boundary current depth. So answering your question regarding the spiral formation, they essentially are linked with the boundary current which is flowing through the basin, and when they become unstable, they form these structures.
The vorticity has to be negative because the coast
Yes.
is on the
Well, so the current is cyclonic. So away from the coast, the velocity will be higher. As we approach the coast, the velocity has to go to zero. So anticyclonic vorticity is generated. So we focus in this bond region to further investigate this spiral formation process. We find that the spiral, the instabilities are generated in the Nile Delta region, and as the instabilities aggregate, they grow in size, and eventually they roll into these eddies, which we are calling spirals. Downstream of Haifa, we find that these eddies start to interact and merge and lead to the formation of large eddies, which are order 100 kilometers in diameter. And these large eddies, as you can see, can transport the coastal water hundreds of kilometers offshore. We also notice these cyclonic filaments at the periphery of these eddies, which form due to frontogenesis. So, to understand how, we have already discussed this a little bit, but how the vorticity is generated in the boundary current, we analyze entropy in entropy balance shown here. On the left hand side, so entropy is nothing but the square of vertical vorticity divided by this number 2. On the left hand side, we have the material derivative of entropy, and on the right hand side, we have all the generation terms. First, we have stretching. If we stretch a vortex by vertical velocity gradient, then it gets enhanced. If we have a vorticity in horizontal, and we can rotate it by a horizontal gradient of vertical velocity, that also leads to generation of vorticity. However, these two effects, for these effects to work, we need to have vorticity in the field. And then we have vertical mixing term, and then horizontal diffusion term. The horizontal diffusion is implicit in the wind scheme that we are third order wind scheme we are using, and these are typically small. And this vertical mixing term can be further decomposed into 3 components, which becomes clear when we vertically integrate this term. So we get this term which is related to surface wind stress associated with vorticity generation by the surface wind. This term is associated with bottom drag, and then we have a dissipation of entropy by the mixing parameterization. So first, let's look at these terms during winter. The first panel shows depth integrated stretching and tilting term. Then we have the 3 components of the vertical mixing term. We find that the most entropy generation occurs because of the bottom drag, and it is aligned with the 200 meter isopath. A relatively weaker vorticity generation is also there because of the stretching and tilting term, and these 2 terms are balanced to a large extent by the viscous dissipation. Notice that the surface generation is negative, but its order of magnitude, it is 2 order of magnitude smaller. This negative production, which we think is because of the eddy killing effect that is included in the bulk formula that we use for modeling the wind stress, as the surface wind stress becomes negatively correlated with the vorticity field, and so there is a net sink there because of that.
Maybe just a comment. When you say dissipation, you always mean horizontal, right? Because in the vertical, you call it mixing.
No, these are because of the vertical mixing. So vertical mixing.
No, the dissipation is vertical mixing or horizontal?
Vertical mixing.
Oh,
the vorticity generation. However, most of the generated vorticity is also dissipated. Similarly, in in summer, we find bottom drag to be the dominant generating term for the vorticity, and in this season we also see interactions along the 200-meter isobar, but shallower interactions are also present. Again, in summer, the boundary current is closer to the depth, and so it can interact.
Closer to what?
Sorry, closer to the coast.
Oh,
Sorry, closer to the coast, so it can interact at shallower depth also. Again, we find significant dissipation in these regions where vorticity generation occurs. Because of the wind stress, there is negative production, but it's much smaller.
so the depth of the mixed layer in the summer is what, tens of meters, like 50
Yeah.
meters? That's why you can get closer to the coast and not in the winter.
Maybe, but I'm not sure of the reason why it is
It's
so.
200 meters deep. If the mixed layer is 200 meters deep, it cannot propagate to the 50-meter isobar.
Yes, right. So if it is sufficiently intensified, then it can propagate. Thank you for the comment. So we also looked at instability mechanisms, but we identify the instabilities indirectly by the energy routes through which they are energized. So basically, so the EKE balance is shown here. We have the time derivative term, then the transport term. These transport term basically reorganize the eddy kinetic energy internally. And then we have the two production terms, shear production and buoyancy production. The vertical mixing term predominantly leads to dissipation of the eddy kinetic energy. So we focus mostly on shear production term and buoyancy production term. Shear production term is shown here. It captures the action of eddy velocity field on the mean velocity gradient and convert the mean kinetic energy into eddy kinetic energy. We have partitioned the shear production term into two parts, pH, which contain the term with horizontal gradient of the mean field, and PV with the vertical gradient. So when there is a EKE generation by pH, so that essentially that is an indication of barotropic instability in the system. And if PV is positive, generating eddy kinetic energy, that is an indication of some kind of paraplanic shear instability in the system. Then we have buoyancy production. Any EKE generation by the buoyancy production means the presence of baroplanic instability in the system, which converts available eddy potential into eddy kinetic energy. The production terms are shown here. Top figures correspond to winter and the bottom figures correspond to summer. We notice that in the shear production, we notice that shear production is dominated by horizontal pH, which is at least 4 times larger than the PV, which suggests that the boundary current goes unstable because of barotropic instability. We find that EKE generation by the buoyancy production is also large, which is comparable to the as you can see, below with pH. And significant, we suggest that the baroclinic instabilities are also active in the boundary current. Also notice that the shear production pH is large at the outer edge of the boundary current, and which is where the boundary interaction also occurs. Essentially, what it means that the boundary current interacts with the bottom topography, vorticity is generated, which in turn goes unstable through barotropic instability. The process is summarized in this figure. This vertical section is in latitudinal vertical direction in the Nile Delta region. This is the Israeli coast. As you can see, because of the bottom interaction, we generate large shear and negative vorticity at the shorter flank of the boundary current, which becomes unstable. This instability grows in scale, and eventually they roll to form spirals. And we also observe these spirals to interact and merge into larger spirals. So so basically this is what I wanted to talk in terms of boundary current instability. Now moving on to the seasonal variability of the surface chlorophyll concentration in the neighborhood of Nile Delta. So here, so in this section, all the chlorophyll analysis has been done by the result that I will show is done by Yotam. So here I have compared the chlorophyll concentration maps during winter, during summer and winter with the flow features that we observed in our simulation. In this map, during summer, we observe an eddy train along the eastern boundary, and similarly, we see these spirals in the same region. Again, in winter, we observe these eddy-like features along the boundary, and also in terms of submeter scale features in the interior. So these comparison again emphasizes the fact that our model does pretty well in capturing the physics that we observe in the ocean. And you can also see there is a spatial variability of offshore of the eastern boundary, which I will which we discuss further here. So to quantify this spatial variability, we pick two regions equidistant from the Nile Delta, one to the east and one to the west, and we plot the chlorophyll mean chlorophyll concentration for multiple years. It is shown. We see that during summer the mean chlorophyll concentration match in these two regions, but they differ